Einstein was right. Webb Telescope reveals emptiness in the universe's earliest epoch. Albert Einstein's theories of relativity and his insights into the fabric of space-time have shaped our understanding of the universe for more than a century. His work predicted a universe that is dynamic, expanding, and governed by the curvature of space and time. In the years following his groundbreaking work, observations such as the discovery of the expanding universe and cosmic microwave background radiation validated many of his key predictions. However, the very early universe, the time just after the Big Bang, remained shrouded in mystery. Now, thanks to the James Webb Space Telescope, JWST, we have begun to unravel this mystery. One of the most surprising revelations of this new era of astronomical exploration is the vast emptiness that characterized the universe's earliest epoch. Once again, Einstein was right. His predictions about gravity, space, and time hold true, even in the extreme conditions of the young universe. Einstein's theories. A new understanding of the universe. Albert Einstein's general theory of relativity, published in 1915, revolutionized our understanding of gravity. Before Einstein, gravity was understood as a force between objects, a simple attraction that grew weaker with distance. Isaac Newton's law of universal gravitation had been the prevailing explanation for centuries. Einstein, however, proposed something far more radical, that gravity is the result of massive objects warping the fabric of spacetime itself. Massive objects, such as stars and galaxies, curve the space around them, and this curvature guides the movement of other objects through space. Einstein's theory not only described the gravitational behavior of objects within the universe, but also made predictions about the universe itself. His equations suggested that the universe could not be static, it had to either be expanding or contracting. This idea was revolutionary because, at the time, most scientists believed the universe was unchanging. Einstein himself was skeptical of his own predictions, and in an attempt to maintain a static universe, he introduced the cosmological constant into his equations. He later called this his biggest blunder, especially after the discovery of the expanding universe by Edwin Hubble in 1929. With Hubble's discovery, the concept of an expanding universe became widely accepted, and the Big Bang theory was born. This theory, supported by the discovery of cosmic microwave background radiation in the 1960s, suggested that the universe began in a hot, dense state and has been expanding ever since. However, what happened in the first few moments after the Big Bang has remained one of the biggest unsolved mysteries in cosmology. This period, known as the universe's earliest epoch, is where the James Webb Space Telescope has begun to provide critical insights. The James Webb Space Telescope, opening a new window on the cosmos. Launched on December 25, 2021, the James Webb Space Telescope is the most powerful telescope ever built, designed specifically to study the universe's earliest moments. Unlike the Hubble Space Telescope, which primarily observes visible and ultraviolet light, the Webb Telescope operates in the infrared part of the electromagnetic spectrum. This is a crucial capability because as the universe expands, the light from distant galaxies is redshifted, stretched into the longer wavelengths of infrared light. Webb's ability to detect this infrared light allows it to see deeper into the universe than any previous telescope, effectively allowing it to peer back in time to when the universe was only a few 100 million years old. One of the primary goals of the Webb Telescope is to study the first stars and galaxies that formed after the Big Bang. The early universe, immediately following the Big Bang, was a chaotic, high-energy environment dominated by radiation and subatomic particles. Over time, this chaos cooled and stabilized, eventually allowing the formation of hydrogen atoms and the universe's first stars. These stars, in turn, began to group together to form galaxies. But how exactly did this process unfold? And what was the structure of the universe in its infancy? These are questions Webb was designed to answer. the early universe, expecting a sea of matter. Before Webb began its observations, many scientists believed that the early universe would be a more uniform place, filled with matter spread evenly throughout space. According to the standard model of cosmology, the Big Bang should have produced a universe that was, at least initially, homogeneous. Small variations in density would have eventually led to the formation of galaxies and other structures, but in the immediate aftermath of the Big Bang, the universe was expected to be relatively smooth, filled with gas and energy. This assumption was based on the data we had from earlier observations, such as the cosmic microwave background, CMB, the radiation left over from the Big Bang, which showed that the early universe was remarkably uniform, with only tiny fluctuations in temperature and density. This uniformity suggested that matter should have been evenly distributed, at least on large scales. However, what the Webb Telescope has observed so far tells a different story, one that is far more complex and filled with unexpected features. Webb's revelations: vast emptiness in the early universe. One of the most surprising findings from Webb's observations has been the detection of vast regions of emptiness in the early universe. Using its near-infrared camera, NIRCam, Webb has captured images of these early epochs, revealing that large portions of the universe were almost entirely devoid of matter. These regions of emptiness, or voids, stretch across enormous distances and challenge our previous understanding of the early universe. The discovery of these voids suggests that the early universe was not as densely packed with matter as scientists had previously thought. Instead, there were significant gaps where very little matter existed. This finding is crucial because it implies that the process of cosmic structure formation, where matter is drawn together by gravity to form galaxies and other structures, began much earlier than previously believed. These voids, in fact, appear to be the early signs of the large-scale structure of the universe that we observe today, where galaxies and galaxy clusters are separated by vast expanses of empty space. The cosmic web, a universe of filaments and voids. In the modern universe, galaxies are not evenly distributed throughout space. Instead, they are organized into a vast, interconnected structure known as the cosmic web. This web consists of long filaments of galaxies and clusters, with enormous voids in between. These voids are regions where matter is sparse, and they can span hundreds of millions of light-years. The cosmic web is the result of billions of years of cosmic evolution, where gravity has pulled matter into dense regions, leaving behind vast areas of emptiness. Webb's discovery of voids in the early universe suggests that the seeds of the cosmic web were already being sown in the universe's first few 100 million years. These early voids, though much smaller than the ones we observe today, indicate that the process of gravitational collapse, where matter is drawn into denser regions, leaving behind empty spaces, was already at work. This process, driven by gravity, is precisely what Einstein's general theory of relativity predicts. According to general relativity, massive objects warp the fabric of space-time, creating gravitational wells that pull in matter. Over time, this process leads to the formation of galaxies, galaxy clusters, and the large-scale structure of the universe. The discovery of early voids by Webb provides direct evidence that this process was already underway in the universe's infancy, confirming Einstein's predictions about the role of gravity in shaping the universe. The role of dark matter in cosmic structure formation. While gravity plays a crucial role in the formation of cosmic structures, it is not the whole story. Observations of the universe, both in the early universe and today, suggest that most of the matter in the universe is not made up of the familiar atoms and molecules that we see around us. Instead, the majority of the universe's matter is thought to be dark matter, a mysterious substance that does not emit, absorb, or reflect light, making it invisible to telescopes. Dark matter, though invisible, exerts a gravitational influence on the universe. It is thought to form the scaffolding for the formation of galaxies and other structures, with ordinary matter falling into the gravitational wells created by dark matter. Webb's discovery of early voids may provide new insights into the nature of dark matter and its role in cosmic structure formation. The presence of these voids suggests that dark matter was already clumping together in the early universe, creating the gravitational wells that would eventually lead to the formation of galaxies. As ordinary matter fell into these wells, it left behind the empty spaces that Webb has now observed. By studying these voids and the structures surrounding them, scientists hope to learn more about the behavior of dark matter and its role in shaping the universe. Reionization and the first galaxies. In addition to revealing vast emptiness in the early universe, Webb is also providing new insights into one of the most important periods in cosmic history, the Epoch of reionization. This period, which occurred about 400 million years after the Big Bang, marks the time when the first stars and galaxies formed and began to emit light. This light reionized the hydrogen gas that filled the universe, making it transparent to ultraviolet light and allowing us to observe distant galaxies. Webb's observations are helping scientists study this crucial period in detail, revealing how the first galaxies formed and how their light reionized the universe. By studying the structures that formed during this time, including the voids and filaments of the early cosmic web, scientists are gaining new insights into the processes that shape the universe. Einstein's legacy, gravity, and the shape of the universe. The James Webb Space Telescope's discoveries of vast emptiness in the early universe are a powerful confirmation of Albert Einstein's theories. They demonstrate that gravity, as described by general relativity, was already shaping the universe in its earliest moments, pulling matter together to form galaxies and leaving behind regions of emptiness. These observations also provide new insights into the